Fortunate to be placed after 3 excellent talks this morning, all of which are about lenses. And today I'm going to be going over some of that story and perhaps giving some new perspectives on how lenses can be understood in a more technical way. And let's go. So the outline is I want to give some motivation and really repeating some of the motivation that we've heard so far, and give some different ways of understanding what we normally call lenses in terms of a kind of morphism between two sets. And then I want to look further into this definition and see how we can look at these ordinary lenses that we're very familiar with in a new way. And then I sort of want to generalize this picture to consider lenses not as morphisms between sets, but rather as some kind of morphism between categories, which maybe hasn't been considered as closely until now. So, motivation. So what is a lens and why should I care? Well, so lenses, as Mike said this morning, are a kind of mathematical structure which aims to capture the notion of synchronization between a pair of systems. And there's lots of different kinds of systems we can consider here. And I guess since the introduction of lenses, and they were originally introduced to solve some view update problem in databases, they've found a variety of different uses, and we've got this whole list of different ways that lenses can be seen happening in the real world. And so each kind of lens that is used here may have a slightly different meaning. And so I want to first go over exactly what kind of lenses I want to talk about. But really the goal for this talk, as I said, is to demonstrate how using some, I guess, diagrammatic methods from internal categories can sort of reveal how lenses are understood as a functor, and also this thing called a cofunctor, which I'll explain what that is. And so the view update problem, and just some terminology to make sure everyone's on the same level. So a system or a database can be modeled as sort of its set of states of that database. And we assume that, I guess we can transition or update between any state of this database to any other state of this database. And whether you think that's a reasonable assumption or not is a really good question, and I'll kind of come back and sort of challenge this assumption later on. And so really the only information that we retain from this update is where we started and where we finished. And again, this is just some terminology. We call the states of S this larger system our source states, and we call the states of this smaller system of this larger system the view. And each view state is somehow determined by a source state. And finally, so just what is the view update problem? So given a source state and some view update where the original view sort of was derived from some source, can we find another source update such that these things are sort of synchronized with each other? In solving this problem, this was one of the original inspirations, and in particular they give us one solution to this is using state-based lenses. And so these are also known as, I guess, very well behaved set-based lenses, as Mike said, or also as sort of lawful monomorphic lenses, as other people have called them. And so state-based lenses, I guess, schematically, we saw a similar picture again this morning, but a state-based lens is really just two functions. So a get function, which takes source states to view states, and also this put function, which does some kind of update process. And so it takes a pair of states, so our S, which comes from our source, which is where we start, and a view, which is where we update to, and this function sort of takes that data and spits out a new source state, which is synchronized with this view state. So this put get law really says that this lens is doing what we want it to do. It synchronizes things. And so this P of SV, this state in S, lies above V in this diagram. And so what's the get put law? Well, the get put law says if we take a source state and look at its view, if we don't change anything, so we go from GS to GS, when we update that, we should also not change anything at all. And so again, that's sort of a reasonable thing that we should consider when working with these kinds of lenses. And finally, the put law says that, well, what's the put law says? It says that we should respect composition of updates. So if we do one update in our view from GS to V, and then we do another update to another view, if we propagate these things to our source sequentially, then that should be the same thing as I guess, composing those updates in our view and then propagating to our source. And so most of our lenses, and particularly the state-based lenses, which I'm going to sort of motivate throughout this talk, satisfy these three laws. And so again, what we've just seen schematically can be written sort of just in an equation form, which is, again, these pair of sets, these two functions, and satisfying some laws written as equations. And here's where things sort of start to get interesting, because here what we now want to consider is if we have these lenses which are a kind of morphism and moving between one system to another system, and we want to do that same process again, so we want to compose lenses, we want to know what their composite is. And as we saw, we've still got this nice little picture over on the board. Composing the gets of two lenses is really straightforward. It's really just composing two functions together. But composing these puts is somehow mysterious and not as clear what's happening, right? So like Mike this morning justified this using some sort of schematic and maybe a little bit of hand waving. And you can sort of justify this by saying, well, in applications, this is what it should be. And if you draw the pictures, well, you can sort of figure out this is what it should be. But there's not to say that there's not another composite that you could have defined that is more correct, or there's sort of no real mathematical justification at this stage as why this should be the composite of these lenses, which we consider as morphisms. And so where that leads me is that we should look at another definition, and again, this is the exact same definition, just written instead with commuting diagrams now rather than equations, is that, again, this lens is two functions satisfying these diagrams, which are equivalent to the three laws for a lens. And the good thing is that once we write these diagrams, immediately what we can say is that, well, these objects, these two sets that a lens moves between, well, they don't actually have to be sets. They can be sort of internalized to any category with products, because all we need to do to write these diagrams and write these axioms, all we need is a Cartesian product in our category. And so I guess we can internalize the definition of a lens to any category with products. And again, so where these diagrams come from, if we really want to motivate where lenses come from mathematically, are just algebras for a certain monad. And so you may have heard this before, as lenses are algebras for a monad, or there's another way of saying that lenses are co-algebras for a comonad. And so when we look at this monad, which takes a function to this projection from the slices of set, the put function just becomes the structure map for this algebra on this monad. And that should really be the end of the story, right? We know now where these diagrams come from. We know what lenses are. And that should be mathematically the whole picture. Except where we get is that we should want to understand morphisms. We want to understand lenses as kind of morphisms between systems. And what we have here is a characterization of lenses as objects in some category of Eilenberg-Moore algebras, right? And so this is not how we think of lenses. We don't think of lenses as some kind of object over a fixed base. We think of lenses as moving between systems that we can compose sequentially. And so there's this kind of there's this conflict between how we think of lenses and how they're described currently in mathematical terms. And so is there a mathematical way of understanding how these things compose as morphisms? And can we develop, using this intuition, some kind of unified framework for incorporating other examples of lenses, such as the split-up fibrations that Mike said should be the way we think of lenses, and also delta lenses, which Zinovi just spoke to us about, as another good way of modeling updates between systems. Question?
You say this is a well-known monad, so like what is it?
I mean, so it's the monad that takes takes an object in this category, which is a function, and assigns this function, and it has a similar action on morphisms in this slice. Does that?
Seems like it doesn't depend at all on t except for the domain.
It doesn't depend on which, sorry?
Like if you change t but you still have the same different domain, then pi1 would be the same.
Composition with g, right?
Right. So this is defined on any possible function into v here, right? And so.
But it seems like it throws out the function, just takes the domain. No,
Yeah.
I mean, it does indeed not depend on G. That's correct. Okay.
Right, okay. There we go. Yeah, so it's this funny kind of monad that's going on.
So it really doesn't depend.
It really doesn't depend. It really doesn't depend.
I don't think it's just that well known. Yes. Okay.
It's well known in the sense that if someone asks you to describe what a lens is mathematically, they'll say it's an algebra for this monad. So, moving forward, how can we look further into what these lenses should really be? So, we remember, just going back a few slides, we've got a lens as these commuting diagrams, and we have this definition, and we say, well, what can we do with these commuting diagrams that makes sense? And so what can we do is, well, if we have a pair of sets, S and V, one thing we can do is always turn that into a category. We can turn a set into a category in two different ways. The discrete category, which is completely uninteresting in this case, and the co-discrete category, which says that we have a category whose objects are given by the set we started with, and whose morphisms are just given by pairs, which tell you which tell you that the morphism starts at this point and ends at this point. And so you think of this as a category whose objects are given by the set, and there's exactly one morphism between each object in this category. So that's sort of what the sets do, and how can we see what the lens is? Well, the lens, and this is quite an interesting, I suppose, observation, is that every lens sort of induces also a category, which I denote by lambda. And this category, again, has objects given by our source states, but now the morphisms are given by pairs S and V. And maybe I should draw a picture to sort of explain what's going on here. But so how we think of an arrow in this category that I'm defining with this span is that an arrow is just given by a pair. And so what's the domain of this arrow? Well, it's just S, which is projecting off the first of this pair, and the codomain is taking the put of this pair. Okay, and that's exactly, when we saw schematically earlier, that's exactly what an arrow, what a lift from this lens is about. And the fact that we can compose these things, right, is exactly telling us that the put law holds, and the fact that this category has identities is saying that the get-put law holds, and the fact that the fact that we actually have composable morphisms and we have this boundary condition is saying that the put-get law holds. And so we can sort of see, and I haven't sort of shown how you prove this, but we actually get this category from the diagrams of a lens. And so the lens laws are exactly the things that you need to say that this category of lifts whose arrows look like this is a well-defined category. Any questions on that? No? Okay. So going further, we have these three categories, and so we want to think, well, how are they related to each other? And how we do that is look at some functors. And so the first functor is easy, right? If we have a pair of sets and a function between them, then that induces a canonical functor between their co-discrete categories, okay? And that's just using universal properties. And also given a lens with comprising of these functions, we obtain two functors as well from this category of list which I just described. And so how this works is, well, this first functor is identity on objects, and so it takes this arrow to an arrow here, and this is living in S, and this is lambda, and this is V. It takes this arrow here down to this arrow here, but now the label, all that really changes is the label. So the objects don't change, it's identity on objects, but the label's changed. So now we have a pair of states in S, which define the morphism in the co-discrete category. And this other functor here, again, it applies G to each of these objects. So we have a G, S, and a G, P, S, V, but we know from the get put law that this is just V. So it assigns this arrow to GS to V, and the label is just again GS V. So that's what these two functors are doing from for arrows from our category of lifts lambda to our source and our view codiscrete categories. And so I guess the moral is that these three functors actually pull together to form a commuting triangle. So if we apply our get to this arrow here, we get exactly this arrow here. And so what I want to say is that a state-based lens, which is given by these diagrams, may be characterized as a commuting triangle of functors, actually, where S and V are again just our codiscrete categories that come from our sets, our source and our view sets. K is just a name for this identity on objects functor, which takes this lifted arrow and sort of embeds it into our larger source category. And G is actually a discrete op vibration. So it takes arrows of this form and this lift here up to here, because of the labeling, is actually unique as in a discrete op vibration. And so really I could stop the talk there, because this is really the main picture I want to put across. But what are some benefits of this? Well, it actually makes composition of lenses immediately clearer, because what we do is we stick two of these triangles together. These two state-based lenses, we characterize them as a triangle. And how do we compose them? Well, we stick them end to end. So this here is one lens, this here is another. How do we find their composite? Well, we just form the pullback of these triangles, of this cospan formed by these triangles. And because, crucially, because identity on objects functors are preserved by pullback, and because discrete op vibrations are just preserved by pullback, then again we get this outside triangle being of the form of a state-based lens, which I've given here. So composition of lenses is really composing functors, which is the easy part, and composing spans, which is the mysterious part of what's going on in the put there. And so this is the same picture here as functors broken up into components. So this is what happens on objects of this pullback, and this is what is happening on the morphism sets. Okay, and so you don't really need to understand that. All you really need to understand is down the bottom here, we get a canonically induced way using universal properties of the pullback and these products to tell you exactly what this composite of a put function should be. And now I've got 5 minutes, so I'll go through this quite quickly. But where can we go from here? How do we generalize this picture of state-based lenses, which are kind of a morphism between sets, but as we've seen, are really a morphism between codiscrete categories? What is the most obvious way to generalize this picture? Well, it would be to replace the codiscrete categories with arbitrary categories, right? And so that's what we do, but just to lead up to that, what is a cofunctor in the title of my talk? A cofunctor really should just be understood as a kind of lifting, okay? So again, we have this similar picture as before, but instead of just a pair, we've got an arrow here now. And what we do is we lift this arrow to something above it, but it's not really above it. All we need to satisfy is that S goes to GS and P of S goes to V. So this boundary conditions are satisfied for this lift. But there's nothing requiring that this K of S alpha, which we lift, has to go back down to alpha, because we don't have a functor here. All we need for a cofunctor is an object assignment and then some kind of morphism assignment going in the opposite direction, and that's where the co comes from. And so this lifting should respect identities and composition. And moreover, when we do actually have a functor here, whose object assignment is the same as this G that I've given here, we require one more thing, and that this arrow which lies above actually does land back on alpha when we apply the functor, and that is what a delta lens is, as described this morning by Mike and as demonstrated in some examples by Zinovi. And so I've just listed some examples of cofunctors there that occur mathematically in the wild. And so every cofunctor can be written as this span of a discrete op vibration and a identity on objects functor. And then those diagrams are just internally what that picture would be. Right, so an internal lens, don't really worry about this top half, but an internal lens is really just a commuting diagram of internal functors. And if you read that sentence without internal in front, a lens is just a commuting diagram of functors such that G bar is a discrete op vibration and K is an identity on objects functor. That should really give you, that should really be what a lens should be, in my opinion. And when those are just small categories, we get what a delta lens is, and we can generalize. We can look at these internal to other categories and see what they could be. And so here are some examples. So again, delta lens is just this internal to set. So we're working with small categories. A state-based lens is just a delta lens between codiscrete categories. And so this K, this lift that we have here, is just given by this thing which takes a pair and assigns an arrow which is a pair of endpoints. A delta lens between monos is just a retraction. A discrete op vibration is again just a special kind of internal lens. And also a split op vibration, which Mike talked about this morning, is surprisingly not a lens between categories anymore. It's a lens between particular kind of double categories. And so that's again one of these fruitful yields of this internal perspective, is that when we look at particular double categories, in particular the double categories of squares which are induced by these source and view categories, then writing out the diagrams and the things that you need for an internal lens gives you exactly what a split op vibration should be. And so just to summarize, an internal lens is a get functor, and the put is actually a cofunctor. And maybe I haven't sort of emphasized that enough, but really this lifting, which is what the cofunctor is doing, is exactly what the put is doing. And they satisfy some axiom which makes that diagram commute there. And really, yeah, a cofunctor is just a span of functors of a discrete op vibration, an identity on objects functor. And so when we put those two things together, we get a lens just represented as this commuting diagram. And composition of lenses, as I illustrated with the state-based lens case, but holds in general, looking at this picture is really just putting these triangles side by side and doing a pullback in the middle. And yeah, this captures a wide range of examples, as we saw on the previous slide, but also provides, I guess, a robust framework, in my opinion, for capturing future examples of what lenses could or should be. So that's it.
Perhaps I'm confused about identity objects and discrete op vibration.
Sure.
I think you said on previous slides that it was K that was the identity on objects thing.
Yes.
The span on this summary slide has the left leg is the identity on objects and the right leg.
Right, okay, so there's a reason for this confusion, and that is also a source of confusion for me sometimes as well. Because this cofunctor is a span, right? There's immediately not an obvious direction to orient this span. So it could go in one direction, in which case the left leg would be a certain, in this case, a discrete op vibration, or it could go the other way. And so what's happening is that when we do a lens as this commuting diagram, the cofunctor, as I've written it, as I've drawn it here, goes from V to S, right? And so when we do this, it goes in the opposite direction. Okay, so the cofunctor goes in the direction of the lifting, I suppose, and the functor goes back in the other direction. So in this way, you can sort of see a lens as a kind of section, except not a section of functors, but a section of a cofunctor followed by a functor, getting back to where you started. Other questions? Yes.
Just to be sure, the notion of cofunctor is not independent. It's relative to a given functor. right?
No, it's relative to a given object assignment between categories. So you don't actually need a functor to define a cofunctor. You just need a way of going from moving objects between categories, and then the cofunctor is sort of the lifting, which goes in the opposite direction to that object assignment.
Is there a standard name for this object?
Is there a standard name for the object assignment?
Yes.
Not that I'm aware of.
So it's not obvious that this deserves the name cofunctor.
I mean, it's called cofunctor because that's what it's been called previously in the literature. It's not something I came up with, but perhaps there's a better name that is more suited to describing what it's about.
Is there another question over here? Yes.
Yep.
Yeah. So I'm trying to see where these three axioms come from when you write it like that. And it seems like put axiom is part of your definition of composition in lambda.
Yes,
Is that right?
that's right.
And then put get
Yep.
comes from one of the commuting diagrams.
Yeah, so this diagram commuting is sort of saying what put get is.
It seems like on the slide where you have those like two morphisms of spans. Yeah, right there on the right one. That's
Yep.
That is put get right there, going around the right square of that.
This one.
If you go to the earlier slide where you have the diagonal pi map, that is very clear. Yeah, right there.
Right, yeah,
That's
so
exactly.
yeah. So that's sort of wrapping up some information which says that this diagram of functors commutes.
And then where is get put?
Get put is saying that you have proper identities in this lambda category. So this category lambda, which we define, if we have an S up here and the identity span going into S and S, so this right triangle commuting is exactly what the get put law is as a diagram. And maybe I can show you that later if you want to see that.
I have not so much a question as a conjecture.
Right.
A prism is a lens in the opposite category.
Correct.
That's true.
Yes.
Amazing.
Well, a state-based lens in the opposite category. So, yeah.
I'm very happy.
Yes.
Who proved that? Did you prove that?
No. I mean, that's just an observation. That's not.
Thanks for the talk. I really like the stuff that you know.
Thank you.
Maybe it's a naive question, but I'm interested in the use of codiscrete categories here.
Sure.
From my name, my theory, without maybe a sense of things. I like to look up to equivalence of categories. Codiscrete categories are equivalent to a terminal category. Why can't we look up to equivalence here? Maybe it's very naive.
I'm not really sure what.
Some categorical construction should be invariant under equivalence, and from that point of view, all codiscrete categories are the same. So, but here you're using constructions that are definitely not equivalence invariant. I think that's easy.
Identity on objects. Yeah, simple.
Yeah. So we're doing this particular choices of pullbacks, and this identity on objects should really be bijective on objects, but we're sort of violating some concepts of equivalence here that mean we.
Any sense of why?
Why? I guess because things. I guess we want to work with things in a nice form, and so I mean, basically all the previous literature on lenses, we're working with lenses in a particular form, right? So like a lens always goes from this particular product, which has elements of this particular pair, and they compose in this particular way. And so for things to work out like that, when we do this abstractly, we want to choose, I guess, particular pullbacks and things like that. But maybe that's not a very satisfying answer, and we should talk about that some more.
Okay. No more questions. Let's thank Bryce again.